Today we'll solve questions of GATE 2026 from gas dynamics topic. So we'll start with the first question of gas dynamics that came, that is question number 21 in GATE 2026. So the question is, the flow at the exit is of this CD nozzle they gave. The flow at the exit, the flow is coming from this direction. The flow at the exit is, so at this exit plane, they want what will be the flow. Okay, whether it is, the given options are over expanded, under expanded, ideally expanded, or subsonic. Okay, the primary use of CD nozzles is to produce supersonic flow, and you can see there is a shock phenomena, so obviously there is a supersonic flow, so you can discard the option D. Okay, so what is this ideally expanded or perfect expansion means? So if you have a CD nozzle, okay, if you have a CD nozzle, the flow as it proceeds from this point to this point to this point from one section. So the pressure, if you mark here as P1, P2, P3, P4, P exit, like that. So the pressure will keep dropping. Okay. So as the flow expands through the nozzle is a flow expansion device. So as the flow accelerates, okay, the pressure drops, expansion takes place. So at the exit plane, let's say this, at this exit plane, the pressure is P, and the ambient pressure, that is the back pressure, okay, the atmospheric or the surrounding ambient pressure is PA. If this P by expanding reaches equal to PA, we call this as perfectly expanded. Okay, we call it as a perfectly expanded nozzle. Fine, it's a perfect expansion. P equals to PA. If that happens, it's called perfect expansion or ideal expansion, or it is called optimally expanded, or it is called adapted condition. Okay, now let's say this pressure, the atmospheric pressure is PA, and the pressure at the exit plane P has dropped to such a value that P becomes less than PA. Means it was supposed to expand up to the atmospheric pressure, but it has expanded more, means the pressure has dropped more. So if P becomes lesser than PA, the nozzle is called as overexpand. So to bring the equilibrium with the atmospheric pressure, okay, so here also it is PA, here also it's PA. So all these particles in these regions, they are at PA, whereas these particles, they are at P, and the flow is coming with a higher velocity. Okay, so in between these particles which are experiencing PA and P, there exists a free boundary. Okay, there exists a free boundary. So P is less than PA, PA will dominate. So the boundary will come closer, giving rise to flow wants to go like this, but it's being turned by certain angle. It's like by a virtual boundary, which we call as free boundary. Fine, we call as free boundary. So the flow, the supersonic flow, is forced to turn into itself, giving rise to an oblique shock formation. So always remember, in an overexpanded flow at the exit plane, you will have an oblique shock waves. Okay, which is the case here. So at the exit plane, we are having the pressure PE, which is lesser than the PA. So there is an oblique shock wave has formed. So the flow is overexpanded. Okay, so obviously it is not the ideal expansion, and let's understand what is under expansion. Okay, so if at this So if the pressure at the exit plane is such that this P is still more than the atmospheric pressure. This internal flow that is coming from inside will push the free boundary like this. Okay? Giving rise to an flow would be turning away from the boundary. So whenever a supersonic flow turns away from the boundary, it gives rise to an formation of an expansion fan. So this kind of expansion fan you will see at the exit plane if this is an expansion fan. So the formation of flow has to expand, right? PE is greater than PA at this exit plane. If P is greater than PA, to bring the equilibrium with PA at this point at the exit plane, it creates an expansion fan. So that flow expands and drops the pressure to the value PA. So, or in such a condition, the nozzle is said to be under expanded. It was supposed to expand up to PA, but it is not expanded. Means the pressure has not dropped to the value of PA. In an under expanded nozzle at the exit plane, you will have expansion fans. In over expanded nozzles, you will have oblique shocks at the exit plane. In a perfectly expanded, neither the expansion fans nor the oblique shocks will be seen. Okay. Flow cannot be subsonic for this nozzle because there is a phenomena of shocks and there are a series of shock patterns. So these shocks will intersect, they will refract, they will hit the free boundary. So this free boundary has the pressure PA. So this flow, when it passes through this shock, it again rises. So to drop the pressure to again equilibrium pressure, there will be a expansion fan. So the incident shock on this free boundary, it reflects as a expansion fan, so that the equilibrium is always maintained along the boundary. So along this free boundary, the pressure is PA. So the flow cannot be under expanded. So the answer to this question is over expanded flow. Let's solve another gas dynamics question, that is question number 64 from GATE 2026. So in this question they gave the data. This flow turning angle is 4 degree. The Mach number ahead of the expansion fan is given as 1.78 and they want this psi to be evaluated. So let's do this. So this is a Prandtl-Meyer expansion fan. So the Prandtl-Meyer function for the given condition at M1 equals to 1.78 from given tables, from isentropic tables, nu1 is 20.15 degree from the tables that are given in question. Okay, so since this is an isentropic expansion, the Prandtl-Meyer function in the region 2 will be nu1 plus theta. If it is isentropic compression, we use minus. It is expansion, so we are using plus. So that is 20.15 degree plus 4 degree. That makes it 24.15 degree. Okay. So using this value of Prandtl-Meyer function, we can find Mach number M2 from the tables. So from given tables, at nu2 equals to 24.15 degree, M2 is 1.92. Okay. So using this Mach number, we can find the Mach angle mu2 as sine inverse of 1 by M2. So this mu2, that is sine inverse of 1 by 1.92, this comes out to be 31.38. Okay. So this mu2 is the angle between the streamline behind the expansion fan and the last mark line. So if this is mu2, this is also mu2. Both these lines are parallel. So this is also mu2. So from this, if you know mu2 and you know theta, you can remove from this mu2 this theta and you will get this psi. So psi will be mu2 minus theta. That is 31.38 degree minus 4 degree. So that will give you psi equals to 27.38 degree. They asked us to round off to the 1 decimal place. So this is 27.4 degree. Okay, that should be your answer. Let's do the next and the last question of gas dynamics in GATE 2026 paper, that is question number 65. So here they gave the flow through a pipe of circular cross section having diameter 3 centimeters, length 20 centimeters. The inlet Mach number is 1.5 and the exit Mach number is 1.1. Clearly the flow is supersonic and decelerating. Okay. So from given Fanno flow table, okay, from table at M1 equals to 1.5, we can find 4F L1 star by D. That is, they gave it like this, into 10 power 4 equals to 1361. Okay. And at M2 equals to 1.1, this 4F L2 star by D can be in times 10 power 4 can be written as 99.35. Okay. In Fanno flow, this L is equals to L1 star minus L2 star. The flow is supersonic and it's decelerating. We can write 4FL by D. You can multiply throughout. So you get 4L1 star by D minus 4FL2 star by D. Okay. These two values we have. We need to find this value. So we get 4FL by D times 10 power 4. If I multiply, I get this 4FL1 star by D times 10 power 4 minus 4FL2 star by D into 10 power 4. So these two values we have. So we need 4F. L is given to us, this 20 centimeters. I'm not converting into meters because we are having the diameter also in centimeters, that is 3. So into 10 power 4 will be equal to, this value we have as 1361 and this value we have 99.35. So evaluating this will give us 4.731 into 10 power minus. So rounding off to 1 decimal place, this would be approximately written as 4.7 times 10 power minus 3. So your blank should be 4.7. Thank you.